I'm here today for Minerva Intelligence, which is a business, startup business in Vancouver, British Columbia, using semantic technologies to leverage human knowledge to solve geologic problems. And in particular, the work I'll be discussing today is how we're developing and implementing taxonomies and vocabularies to solve these problems, building on work that's been done over the last several years, developing a lot of what we've been hearing about this morning, these evolving collections of data, geologic data that uses standardized vocabularies coming from the work of the IUGS CGI, the Inspire infrastructure, and also from the One Geology program. So we're actually trying to take some of these things and put them in action for some practical applications. So the motivation for this is how do we utilize human observation data in artificial intelligence applications? And the problem we're facing in large part is that we're dealing with descriptions that are generally written by geologists who are using categorical data terminology to describe things they're seeing in the world that are to some extent subjective and depend on the context of the observations they're making. And so the solution we're working with is trying to develop machine actionable vocabularies that are consistent in their semantic intention so that we can use them for reasoning with automated systems. And I'll finish with some examples of a couple of vocabularies that we're using. So just to sort of set the stage, I just wanted to present, here's some kind of typical geologic descriptions. And I don't want to really dwell on exactly the details, but I've highlighted in yellow all the various kinds of technical terms that get used in these things that need to be defined carefully in order to be able to reason with them in a machine system. And so the question is, how do we get these terms set up so that we can use them for automated processing? The issue is that human language, as I mentioned, is not necessarily precise. What a word means kind of depends on who's using it and the context they're using it in, and it'll vary from community to community. And another issue is that for any given set of concepts that have some kind of hierarchical relationship, there's different ways you can look at a concept hierarchy. So for instance, a mineral like galena, which is a lead sulfide mineral, you could view it as a cubic mineral first, and secondly as a sulfide mineral, or the other way around, and set up a hierarchy either way. It's equally valid. Or with a rhyolite tuff, you might think of it first of all in terms of the chemistry. In the TAS classification, it's rhyolite, but that depends on its composition. But you might also think of it first in its genetic context as a pyroclastic rock. So there's these different ways of looking at things that are important, that might be important depending on what you're trying to do. So to tackle this, the idea is we need to develop precise definitions for the terminology we're using and use it consistently. And going back a long way, this is not exactly a new idea, but build the definitions by first starting with binding to a more general concept and then specifying the properties that differentiate the concepts that have the same genus underneath those. So, and using a consistent set of properties to differentiate the siblings that have the same parent or the same genus. So as an example, let's think about, in the categorization of plane figures. We have a quadrilateral, which is a figure that has 4 sides. A rectangle is a quadrilateral where it has 90-degree angles between all the sides. We can then make a more specific category of a square, which is a rectangle where all the sides have the same length. So each one of these layers inherits all the properties from the one before, but adds some more specific property specifications. In the realm of geoscience, then, if we think about things like the mineral categories, are specified based on a collection of properties like color, hardness, chemical composition, and crystal structures. Or if you're talking about depositional environments for sedimentary rocks, you're developing categories that are based on properties like climate and water depth. There are the depositional processes involved, the relationships of the location to mountains and lakes, things like that. So there's these sets of properties that are associated with these definitions. And you can think of these dimensions of differentiation for your categories in these schemes as defining a concept space. So we have a simple concept space here for minerals based on chemistry, crystal system, and hardness. And if we look at the regions in this space, are the categories we're interested in. So each different mineral will plot in a different part of this abstract space we're thinking about. So this is a way to think about it. And what we want to do with our vocabularies is partition that space so we don't have overlapping regions that have the same word that we're talking about. In other words, ambiguous meanings. So as we construct these vocabularies, then we have the properties that specify the concepts. Those properties are specified by terms in a lot of cases, and those might themselves be complex terms that also then can be analyzed into differentiating properties down to the level of what we might call atomic properties, which just have one differentiating property axis. So things like, in the case of minerals, let's say hardness and density. So there's one thing we're measuring. And by breaking down these definitions to get down to the level of basing it on a set of these atomic properties, we're generally dealing with property values that are simpler to specify and less problematic to get agreement on in terms of what we're meaning and to be unambiguous about. And so if you build these complex definitions up from the atomic concepts, then you end up with definitions that are more amenable to machine processing. And what we can do then with these things is this asserted set of hierarchical property values that we use to define the concepts can then be used to infer the hierarchical relationships between the concepts in a vocabulary. And you end up then with a vocabulary that's easier to maintain, and you can account for these multiple views of the hierarchy, depending on, because all the parent-child relationships are inferred from the property values. And you can validate your property hierarchy to be consistent with your knowledge of how things are supposed to work. So you can actually test your definitions to make sure they're logically coherent within that framework. And so as an example then, if we move into rock type taxonomy, what we have here is, this is based on the IUGS CGI simple lithology vocabulary, which is also used in Inspire. We've added some terms in here to extend it a little bit. But you start out with a list of what are the things we're interested in. And here's a long list of kinds of rocks. And what we have to do is figure out, okay, how are we differentiating all these different kinds of things we're interested in? And so from that, we develop a set of properties that we're looking at. So chemical category, consolidation, the constituents, what kind of fabric the rock has, a genetic category, grain size, etc. And each one of these properties then has an associated vocabulary for specifying that property. Those are over there on the right-hand side. And some of these vocabularies are pretty simple, like consolidation. Well, something can either be consolidated or unconsolidated. And some of the properties, like fabric, can have a fair amount of structure and hierarchy within the values for that property. And so then, based on having these properties like this, we can then define the different kinds of rocks within this framework. So there's a couple of examples here. And in both cases, the genus, the most general property we're dealing with is rock material. So that's up at the top. And then each one of these has a set of logical criteria that allow you to differentiate a breccia or a phonolithoid from a generic rock material. And this allows you to differentiate the instances of that kind of rock, the same kind of definition we just saw. And so then, building these kinds of definitions then, we can actually infer a hierarchical set of relationships between different kinds of rocks. And so, in this case, let's say sedimentary rock appears twice in this hierarchy. Once where if you consider first in terms of consolidation, something's a rock, and then the genesis, it's a sedimentary rock. But you could also approach it by thinking about the genesis first. Well, it's sedimentary material, which would be either rock or unconsolidated material. And then if it's consolidated, it's a sedimentary rock. So likewise with carbonate sedimentary rock, it appears in a couple different places. And that depends on the ordering of the properties you use to build your hierarchical relationship. And how you think about it depends on what you're trying to do. So if we move to another vocabulary we're working with is the land use vocabulary. And this is built on the Hilux vocabulary that's being used in Inspire. And again, we have a collection of land use categories that we're interested in. How are they differentiated? And so you can define a set of properties that are used to distinguish these things and build vocabularies on those properties. And then from that, infer a hierarchical organization of all these kinds of land use that allow you to set up a logically coherent taxonomy. So the basic approach here is to find the terms based on genus and differentiates. It requires some discipline and logical thinking, and I find generally just writing down the definitions in English to start with is mostly what we're doing at this point. That's what all the CGI vocabularies are built on. But once you do that, you can then start implementing them in something like OWL that lets you then test your inferencing to see if your structure of your vocabulary is consistent, and then you can start using that for inferencing. So the terms that have the same genus, the same parent, have to be unambiguously differentiated. In other words, you don't want to have terms that have overlapping meaning. And then the idea is to build the differentiating properties with progressively more atomic kinds of properties to make the definitions unambiguous. This lets you then infer the taxonomy of your concepts in the vocabulary from the definitions you build. It enforces the logical coherence within the vocabulary so that you don't end up making inferencing nonsense. And you can also add new concepts without rebuilding the whole taxonomy because it just requires maybe extending your property vocabularies. So thanks. There's a couple other talks today. Earlier this morning, my colleague Gio Roberti talked about applying this scheme for hazard assessment. And the next talk by Jake McGregor will be looking at the applications for mineral exploration and hazard mapping in a little more detail about how the procedure works. So thank you.
Thank you very much. Any question? There's half a question.
Yeah.